So it was the last presentation of the day. Jürgen said he won't keep me to time, so I can go as late as I want. Or maybe finish early. So we're talking about recording image streams. And I'm a software guy, so we're talking about hardware, just to make it confusing. So my agendas are always quite straightforward. Why do we care? Yeah? What are we talking about? So define it. How do we do it? And finally, what's new, which is the bit you have to wait till the end for. So recording image streams. Why do we want to do it? Really, there are two different reasons. One, you need no processing, or you're going to do your processing offline or not inline in some way. So, no processing. Maybe it's visualization. Maybe it is recording data for training. We see this in military applications sometimes. It could be dumb security, the dumbest security, where you just record images and then you say, "No, we had an incident last night at midnight," so we scroll back to midnight and we see what happened. Then it gets a bit more interesting. Debugging a process that's being done by a human, so a human that's putting something together. This comes into training as well. So I said military, it can also be industrial. So imagine you get an expert to put together a product, and then you get a new guy and you record him, and you show him what he did wrong, and you train him again, and he gets faster. And it's a way, it's what we used to call time and motion. It's a way to see how long things take and how you do it, how the experts do it. Review failures. Think about the bottling plant here. There's one thing that can go wrong in a bottling plant, which is the glass breaks. And then you have to clean everything. The problem is, when you actually see the broken glass, it already happened some time ago. So putting a vision system in to detect the broken glass, you don't know where it happened. So sometimes doing some recordings just to see where did it happen is the first part of it. Next one, broadcast, especially sports. Think about finish line cameras for athletics, for horse racing, things like this. Also football. Football is probably the one you see most. Being able to do an instant replay. You don't do that with a video. You do that digitally. And you can be a lot cleverer than has been possible in the past, where you can track players, but the first thing is you have to be able to get the data. You have to be able to get the image data. And then finally, the things that machine vision cameras are good at that other cameras are not so good at. So this is the high speed, the very high resolution, accurate triggering, and things that are not visible. You know, the infrareds, the thermal, and things like this. Or offline processing. So you're not having to process in real time, but maybe you have an event that happens and you'll process sometime later. So you're recording the data for later processing. Another one, this is one that we do quite a lot, saving data so that you can develop your processing. So before you start your planning your image processing, you create a load of data. It's your training data, your test and training set. So what do you have to do? Well, you either save to RAM or you save to disk. It's quite straightforward. But what are the implications? RAM is fast. We know RAM's fast, but it's also limited and not persistent. It goes away. So I picked something fairly normal. So I picked 8 gigabytes. This is DDR4, so DDR means double data rate. So for every cycle of 1400 megahertz, we get 2 operations. So yeah, 8 gigabytes is fairly normal. 16 gigabyte sticks are fairly normal. Windows 10 Pro supports, 64-bit, supports up to 512 gigabytes. That's a good amount of recording. That's, 512 gigabyte hard disks were big not many years ago. But that's not often where the limit comes from. Usually it's the motherboard. Usually it's a hardware limit. So we said 1400, it's a double data rate. I actually made a mistake on this slide. It's not 2.8 gigabytes per second, it's 2.8 giga operations per second. So you then have to multiply by 8 gigabytes and you get something like 20 terabytes a second. But it's not persistent. When the power's off, everything's gone. So maybe you still have to save this data unless you really don't care. But you may still have to save down to disk. This is from a data sheet from a Supermicro motherboard. So it supports 12 slots up to 192 gigabytes. This is the hardware limit. So no matter what Windows will support, look at what the hardware supports, what the motherboard supports. Okay, disks. This is straight from the Samsung website. Samsung are often the fastest. They're not paying me. They just are. What do you get with disks? Well, you get the old disks, the spinning platters. These are magnetic, so they have some ferrous element. They have some iron element, so they get called rusty memory. It's a nice name because it's kind of old technology these days. These are largest and slowest. 10 terabytes was the biggest I could find recently, and the fastest I could find was 200 megabytes a second. That's very fast for a spinning platter. Certainly you don't find 10 terabytes and 200 megabytes a second. You might find 70, 80, 90 megabytes a second. But that's still an improvement on 5 years ago. So move from spinning platters to SSDs, typically smaller, usually faster, almost always faster. The biggest I could find was 4 terabytes. These are expensive. But you can quite easily get to 500 megabytes a second. Typical is maybe 200, but 500, again, this is a Samsung one, 500 is possible and easy to get to. There are also hybrid drives. These are usually not appropriate. Hybrid drives have an SSD part and a spinning platter. So you get the speed and you get the size. But you also get both problems. It's good for sequential read-writes. It's not good for a sustained write. If you're doing a sustained write, it's no better than an SSD. You're not gaining anything. So, we looked at RAM. RAM's so fast we don't have to think about it. It's faster than any camera. It's really not going to be a problem. So if you can use RAM, it will be fast enough. So we look at disks. What about compression? If you can use compression, what you're doing is you're taking some of the load off the disk and putting it on the CPU. Somehow you're converting the data to reduce the load on the disk. Next thing, whatever kind of disk you have is addressed in terms of sectors. A sector would be like A here. It's the smallest addressable section of a disk. And since about 2011, a sector has been 4,096 bytes. That's standard. It's true. As it's the smallest addressable section, if you had a 5,000 byte file, it would cover 2 sectors. And the rest of the sector is written as packing. So you can think of this as writing zeros to fill up the rest of the sector. So we're writing data even when there is no data. This is wasteful. Unless you're lucky enough that your image is exactly a multiple of sectors. But we're talking about 4,096 bytes. It's not a huge amount. The problem we have is that an image stream is many images. So we're multiplying up that packing data. So it becomes significant. Next, most recording systems use DIRECTSHOW. DIRECTSHOW gives you an easy access to a lot of free and paid-for codecs. So you can get easy compression. And the nice thing is that DIRECTSHOW is a Microsoft standard, and everyone keeps to it. It's nice. You know, if you want to play back, all the media players will use DIRECTSHOW. So that's easy. Let's use it. But there are problems. And these are problems related to recording. It only supports 8-bit data. So maximum 256 levels, whether it's mono or RGB. And it has some overheads related to the number of files, number of images, so there's some kind of start and stop overhead, but also a maximum recording bandwidth. So depending on the size of your images and the rate of your images, you find hard limits. So we have this problem. We have cameras getting faster, cameras getting higher resolution, we have disks getting faster, disks getting higher capacity, and in the middle we have DIRECTSHOW causing a bottleneck. I think you guessed the solution now. Blah, 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 blah. Why not create an unlimited method of saving, where we don't have to do packing? That would be nice. We can use the full performance of the disk there for the data. And we'd like to have high-bit data if we want it. So what do? This is the advert. You've had the facts. This is the advert now. This is the only sales part. CVB, Common Vision Blocks. We have a tool called CVB Movie. The latest version in CVB 2019, we created our own container, not an AVI container, not a DIRECTSHOW method, so we can optimize for speed. If we format the data into chunks that are the same size as a sector, there is no packing. So we optimize writing for speed. Disk space comes in as well. It's not really a priority, but we optimize for speed. But we have to stipulate some things. We say no compression. We could do this in the future, but we've said no compression. The data must fit into a whole number of sectors. So this puts some limits on, or limitations, on what the image size can be. So we're not allowing a free choice of image size. And we will not keep to media player compatibility. This is DIRECTSHOW. So we're not keeping to DIRECTSHOW. So what do we get? We get the data optimized to the disk. We've put the data in a format that can go to disk as quick as possible. So now the only limitation is the disk. What do we get? These are real customer applications, by the way. 15,000 frames per second. If you have something moving at the speed of sound and you take 15,000 frames a second, it moves 2 centimeters between frames. That's pretty fast. 3 gigabytes per second you can have a better feeling for. But as these are real customer applications, we don't believe we found the limit yet. And the limit is likely to be the disk, unless there's some memory bandwidth in between that gets in the way. But that's how far we've got. So, thank you very much.
Thank you, John.